Thank you very much. I'm Barry Boulding. I want to apologize because in this talk I don't have a single picture of a rack. And we have beautiful Cray systems, but I'm doing a talk that is not concentrated on our product portfolio today. Instead, I want to talk about some of our customer use cases. We've been talking for a long time at Cray, and I think the community has, about how data analytics and supercomputing are going to converge and eventually going to bring us more insightful answers to the questions that we pose both in science and business and in technology. And I want to talk a little bit about some customer examples that are beginning to step in that direction and beginning to bring those two pieces together. So IDC likes to call this area high-performance data analytics. I'm not sure I like that term, but I thought I'd use it as an homage to IDC. But it certainly does involve HPC, or as Cray likes to call it, supercomputing. It does involve data. It does involve analytics. So. I read a recent article on Medium about kind of the age we're entering in big data analytics, and they talk about that we just are passing out of the age of mobile, the era of mobile, and I think that's true. Even in computing, in high performance computing, for the last 10 or 15 years, it's been about miniaturization. It's been about increasing the core counts and really making devices smaller and smaller. It's the same technologies that have driven the mobile technologies, and the consequences are that we're now able to collect so much more data. And the article talks about that we're entering really an age of context, where we're beginning to have so much data accessible to us, and we're beginning to interact with that data through things like Fitbits or through our phones, that we'll be able to live in a contextual environment, that as we walk around a shopping mall, we'll be able to get feedback about what sales are on for the types of devices that we like to buy. And living in that contextual environment, kind of Minority Report kind of contextuality. But what I really want to talk about is that's an interesting era to be in, and we're going to see a lot of big data analytics converging with computing. But really, that type of age of context is really about interpolating data. It's about bringing together data that you already have posted. You've basically bought lots of things in a certain area, and now you're getting feedback on where you've provided input, and that's really interpolative. But I think what I'm most interested in, I think Cray is, because Cray is continually looking 5, 6, 7 years down the road to look at what our largest customers and most demanding customers want to do, is really what the next age is. And I'd like to think of that as the age of insight, where we're actually extrapolating the information. And I don't think we're there yet, but I do think that we're going to be bringing more technologies to bear in this area and doing more extrapolation in both commercial, government, and I really want to talk a little bit today and get your feedback in the panel on this age of insight. So Cray has, for several years, been showing this vision that we have of modeling the world. Cray is about solving the biggest grand challenge problems in business, science, and industry. And we talk about the math models, the computational models, the arithmetic models that we've for so long built systems and created architectures that optimize the applications for. And then we've talked about data models and how today we actually provide infrastructures that also provide analytic solutions at the highest end to solve very complex problems such as threat analytics, as Bob was talking about, those endpoint problems in security where the supply chain is putting at risk. We work with partners with our Eureka platforms to look at how to do threat analytics on those endpoints, and that's really a hardcore analytics type of problem. But as we move into this age of insight, we're really talking about being able to dynamically mix and match and bring to bear on problems both the mathematical or computational simulations and the data that we derive and the contextual data that we derive, and then to bring a class of infrastructures to bear that really are optimized for that. And Cray is all about adapting the architecture to the application. Rich Loft talked earlier today about, exascale really, is just terminology. It's about getting the most efficiency out of the infrastructure that you have, whether it's software or hardware, and getting the best performance, the best outcome for your result. And that's what Cray is all about, adapting the infrastructure to the applications. And in this data-intensive world, that's going to change. Those infrastructures are not going to be the same infrastructures. They may have a lot of similarities, but you see technologies like the burst buffers and the data warp that Cray has that are all built around streamlining the data movement in and out of our systems, and it's really to attack that central problem. Now, Cray is a little unique in the space. I mean, I could talk about our leadership in supercomputing. We definitely have that leadership place today at the high end of supercomputing, but we also bring a huge number of differentiators to bear to this problem, and so this is really context for my expounding on this topic. We design systems from the top down. So we design to the most challenging customer problems, and we design infrastructures and solutions. And then we try to bring those technologies down to the mid-range, to the small business, to the cloud. We bring those hardware and software technologies down from the high-end scalable solutions, whether that's a high-end analytics solution that is solving a Spark-based problem, or whether that's a high-end, highly scalable 50,000 core infrastructure for doing highly scalable arithmetic problems and simulations. We also then, as I said, I'll just repeat myself, we really are focused on TCO and return on investment. So it's about the application. What is the amount of performance you get per dollar for the application that you perform? We design our systems to those specifications. We also, that's not a hardware problem, that's also a software problem, it's an ecosystem problem, it's a partner problem to really enable these programming environments and build solutions that meet those demands. And then finally, the community. It's working on the co-design. Since we're looking 5, 6, 7 years out, it's really about building those partnerships will help us meet this age of insights computational infrastructure needs. And actually now I'm going to transition into those customer engagements that we have that are really on the cutting edge of helping us to learn what infrastructures are going to play best in the age of insight. So one of those that we just announced is with the Alan Turing Institute in the UK. This is a consortia of universities, and we've actually, through one of our university partnerships and through the UK government, EPSRC funding agency, we've actually entered into a collaboration where we're going to be helping some big data analytics workloads to work on the Archer systems at Edinburgh and part of the EPSRC. This is a really interesting institute because it's combining both university, commercial, and government academic partners. In fact, they've also announced a partnership with GCHQ as part of the Turing Institute as well, and that's a public announcement of a very focused government entity that does look at things like threat analytics in a very concerted fashion. So this is very new, we just announced, so no results from this engagement yet, but certainly a desire on Cray's part to learn what the partners involved in the Turing Institute are seeing as their challenges for the age of insight. A quote from Peter Grindrod. He had a TEDx video that he did talking about the Turing Institute, and one of the quotes that I really liked most was, they don't just want insights, they want actionable insights. And I think that's key to a really productive age of insight that we want to get to over the next few years with compute and analytics. Another example is one that comes out of a more traditional area of supercomputing. It's really highly rapid genome assembly, and this is a combination of using infrastructure and architectures, both hardware and software, to really redesign the software for the modern age and really make it a parallel software architecture. So a group based largely out of Berkeley Labs and a few academic institutions, Kathy Yellick and a number of others, took a code called Miraculous, and they actually rewrote it for a highly parallel environment. We're able to get a factor of 170 speed up on the original Miraculous code, and because of that, do a human genome simulation in under a full genome assembly in under 9 minutes. The really interesting thing is that using this is their quote, that the HIPMER, or high performance Miraculous technology, enables for the first time the assembly throughput to exceed the capability of the sequencer in being able to do the assembly as fast or faster than the sequence can produce the data. And if you think about the analytics this opens up, if you're looking at things like fast-spreading viruses, if you're looking at being able to do real-time medicine in a crisis situation, this is the type of technology you need to be able to do and get those turnaround, and to combine the analytics with the high-performance computing. By the way, they were using UPC in their code to do single-sided messaging, which really was matching the application to the architecture and being able to get the scalability and speed up out of the application. Another example from the life sciences on actually the only product I mentioned on here I did a typo on. It's an XC30, not a CX30. So the only Cray product I actually mentioned in the whole presentation, I mistyped. So Magnus is an XC30 at IVEC in Western Australia, and a really great other example of doing genome analysis and looking at morphology, looking at genome was with the whiteflies in Africa. They actually have a case where 34 different species, actually all morphologically identical. They can't tell the difference unless you actually sequence them. And to be able to fight this whitefly, which devastates the agave crops in Africa, they had to actually do genetic sequencing and investigate the differences in these species. So really a massive problem and a new project to really bring change to the farmers in Africa. But again, very analogous. If this were a virus that were highly contagious, you get into this very fast analytics and simulation environment. Another example is protein folding. And this is a classic area of HPC where systems, typically people build complex models, they do molecular dynamics simulation, and they're able to follow a cycle where they generate models, they do simulation, they compare the models to reality. The real problem is today, this has evolved from the days when I used to do it as a graduate student, to where they're actually doing such complex long simulations that they can't analyze all the data they collect. And because of this, they're actually using analytics techniques to assimilate and bring down the complexity of the problem. So they're actually, if you go into this reference, you can see that they're actually using analytics techniques to reduce these vectors that represent the trajectories of all these models. And so they're doing many, many trajectories, and they're using linear algebra to reduce down the number of trajectories and be able to look for similarities. They lose some of the data when they do that. They're able, through complex linear algebra, they're able to retain about 90%, 95% of the information, but they're able to look at far more vast quantities of data. So this type of technique, combining analytics and high-performance computing, is really critical to future questions about how proteins fold. And that group actually, based out of, oh, I was supposed to have a picture there. Oh, didn't show. Oh well. It was a nice graphic there. I was going to make a joke because it went way back to 1998, and when I was doing it, it was even further back than that. So when I was doing those type of simulations. The last example is with the DOE, and Cray is working with NERSC on a number of projects. They have a number of places where they see analytics and computing really coming together and facing challenges. So we have a collaboration with LBL and the AMPLab consortia to look at some of these areas and try and work both the computational and analytics side. They see a number, they actually have a list far larger than this of different problems that they see where analytics and computing are going to be aligning. Here's just a couple of examples, sort of an eye chart, but the one that we've been working the most with them on is actually the bioimaging one in the middle, the bioimaging simulations. So, last quotes. So the last quote that I'll bring is actually from the August Computer magazine by the IEEE. John Feo and a colleague had a series of nice articles that they edited for that on high-performance multi-threading combining with simulation. And they make a statement. Current HPC machines are optimized for scientific simulations, arithmetic-intensive workloads, and regular computation, whereas data analytics require hardware optimized for bandwidth, throughputs, concurrency, and all-to-all communication. Well, when I read that, what I see is Cray's philosophy of matching architectures to applications. But I'd like to change the quote. So I have my own version, which is the age of insight will require hardware and software infrastructures and ecosystems optimized for all of those, for the data analytic and the data intensive simulations with both regular and irregular data access and throughput, concurrency, all-to-all communication scalability. That's the infrastructures we need to build because they need to adapt to the types of applications we're going to face over the next 5 or 10 years. Thank you.